Bayesian decision theory losses and risks. It may be the case that decisions are not equally good or costly. A financial institution, when making a decision for a loan application, should take into account the potential gain and the loss as well. An accepted low-risk applicant increases profit, while a rejected high-risk application decreases loss. The loss for a high-risk applicant erroneously accepted may be different from the potential gain for an erroneously rejected low-risk applicant. The situation is much more critical and far from symmetry in other domains like medical diagnosis or earthquake prediction. Let us define action alpha I as the decision to assign the input to class Ci and the lambda ik as the loss incurred for taking action alpha I when the input actually belongs to Ck. Then the expected risk for taking action alpha I is the R of alpha I conditional x, which is equals to the summations of lambda ik times probability of Ck conditional x. And the summation is summing for all index k starting from 1 to k. So this is the expected risk for taking action alpha I. And we choose the action with the minimal risk. That is, we choose alpha I if R of alpha I conditional x is equals to the minima of R conditional alpha k conditional R of alpha k conditional x, where the minima is chosen among all the possible k. Now let us define k actions alpha I starting from 1 to 3 until k, where alpha I is the action of assigning x to Ci. In the special case of the 0-1 loss case, where alpha ik is equals to 0 if I is equals to k, alpha ik is equals to 1 if I is not equals to k. All correct decisions have no loss, and all errors are equally costly. The risk of taking action alpha I is R of alpha I conditional x, which is equals to the summations of lambda ik times the probability of Ck conditional x, where the summation is summing for all k starting from 1 to capital K, and which is equals to the summations of P of Ck conditional x, where we summing for all those k which is not equals to I, which is, by definition, equals to 1 minus the probability of Ci conditional x. Because the summations of the probability of Ck conditional x summing for all class k is equals to 1, thus to minimize risk, we choose the most probable case. In later chapters, for simplicity, we will always assume this case and choose the class with the highest posterior, but note that this is indeed a special case and rarely do applications have a symmetric 0-1 loss. In the general case, it is a simple post-processing to go from posteriors to risks and to take the action to minimize the risk. In some applications, wrong decisions, namely misclassifications, may have very high cost, and it is generally required that a more complex, for example, manual decision is made if the automatic assistant has low certainty of its decision. For example, if we are using an optical digit recognizer to read postal codes on envelopes, wrongly recognizing the code causes the envelope to be sent to a wrong destination. In such a case, we define an additional action of reject or doubt, alpha k plus 1, with alpha I starting from 1 to 3 until k, being the usual actions of deciding on classes Ci, I starting from 1 to 3 until k. Now, a possible loss function is lambda ik equals to the following three cases. Lambda ik may equals to 0 if I is equals to k. Lambda ik may equals to lambda if I is equals to k plus 1. Here is the capital K plus 1. lambda I k may equals to 1 otherwise, where lambda is between 0 and 1 is a loss incurred for choosing the capital K plus first action of reject. Then the risk of reject is alpha, the expectation of alpha capital K plus 1 conditioning on x, which is equals to the summations of lambda times the probability of ck conditioning on x, where the summations summing for k starting from 1 to capital K, and it happens to be lambda, because the summing of all those probability of ck conditional on x is equals to 1. And the risk of choosing class Ci is r of alpha I conditional on x, which is equals to the summations of the probability of ck conditional on x, summing for all k, which is not equals to I, which is equals to 1 minus the probability of Ci conditional on x. And the optimal decision rule is to choose Ci if r of alpha I conditional on x, which is less than r of alpha k conditional on x for all k not equals to I, and r of alpha I conditional on x, which is less than r of alpha k plus 1 conditional on x. And reject if r of alpha k plus 1 conditional on x, which is less than r of alpha I conditional on x, where I is starting from 1 to 3 until k. And given the loss function of equation 3.10, this simplifies to choose Ci if the probability of Ci conditional on x is greater than the probability of Ck conditional on x for all k not equals to I, and the probability of Ci conditional on x is greater than 1 minus lambda, and reject otherwise. So this whole approach is meaningful if lambda is between 0 and 1. If lambda is equals to 0, we always reject. A reject is as good as the correct classification. If lambda is greater than or equals to 1, we never reject. A reject is as costly as or costlier than an error.